we're going to do now is talk about anatomy and development, and this is the last segment of the notes on evidence of evolution. We are going to take a look at the different types of anatomy that we see in species and how this anatomy leads us to understand that they are part of a transition fossil or that they are related to a different type of species. You have this information on your copy of your notes in part 3. So what we're going to look at here is this term called homologous structures, and homologous structures comes from the word homo, meaning same. And so when we look at these vertebrate limbs, we're looking at structures that are all similar. If you take a look at the color coding, for example, all of the yellow-orange coloring represents the same structure in each of the limbs. And all of the purple represent all of the same structure in each of the limbs. So they've been modified over millions of years to represent the structure needed for that organism to perform its task with its structure. But all of them all have similarities in the way those structures are aligned within the body.
From my earliest days in the anatomy lab, I've always enjoyed tracing the connections between humans and other members of the animal kingdom. And those ties sometimes present themselves in unexpected places. When I walked into the anatomy lab for the first time, I was sort of scared about what I was going to see, what I was going to feel. But the reality is, after the first few weeks, that fear turns into a sort of a cocky self-confidence. And these things, when you dissect them, it doesn't look very human. It kind of looks like a wax model in a lot of ways because it's been preserved. But then you hit the hand. And for me, as I unwrapped the gauze and revealed the palm, the fingers, the fingernails, something else hit me entirely. And that was a deep sense of connection. A connection to another human body lying on that slab. This was not a wax model that I was dissecting. This formerly was a person who lived a life just like I am living now. The structure of the hand is remarkable and complex. Its muscles, tendons, and bones allow us to shape the world around us. But it turns out this basic structure is not unique to humans. In fact, it points to our connections with other animals. By the 19th century, scientists were documenting the similarities among the limbs of vertebrates. Sir Richard Owen was an anatomist back in the 19th century. He was fortunate to be an anatomist in an age of discovery. And so people were coming back to London with new and oddball creatures for him to analyze. And in analyzing all the different creatures that were brought to his laboratory, he found common patterns. Although the shape and structure of each limb was very different, Owen started to see an underlying unity. It was as if the same set of bones was being squashed or extended to perform different functions. Here's a dog. Dogs, run and jump. What do you have? One bone, two bones, little bones, and then the digits, the equivalents of the fingers or toes. And, of course, here's a bird. It flies. Its limb has been modified into a wing, and it has one bone, two bones, lots of bones, and then digits. The amazing fact is, in each of these creatures, the architecture is largely the same as ours. Owen didn't know why creatures had that pattern. It was a mystery to him. It was sort of a mystical concept that there's this common architecture behind all animals. It really took a new insight, an insight from Charles Darwin, which basically said the reason why animals have this common pattern is because at some time in the distant past, they all shared a common ancestor that had a version of this pattern too. As far back as 375 million years, we've found fossil evidence of a creature that has this pattern. It's fish-like, and it's just beginning to make the move onto land. My team found one of these transitional animals, called Tiktaalik, after 6 years of exploring an island in the Canadian Arctic. Remarkably, its fin had the beginnings of the one bone, two bones, many bones, and digits pattern. It's good evidence that the basic form of this complex and quintessential piece of human anatomy, the hand, emerged from the fins of ancient fish.
Okay, so again, you're seeing a little bit of a repeat of what we've talked about already in terms of transitional fossils. Well, in transitional fossils, we're able to find these homologous structures. There's also something called vestigial structures, and a vestigial structure is, for example, something like your appendix or your tailbone. These are structures that have been useful in previous ancestors, but now have no use in our current species. For example, when we look at the tailbone, we don't see tails on humans unless you see, in this particular case, on the left, a mutation where the tail actually is growing out of the human. So tails are a vestigial structure. It's a structure that we have evidence that in our previous ancestors that we branched off from, that they at one point had a tail, but over millions of years, the tail for our species was not used and eventually disappeared, but the remnants of that tail are still left over in the structures that we have internally.
Gingrich's early interest in primitive land mammals eventually took him to Pakistan. It was there that he made the kind of find most paleontologists only dream about. A fossil that would rewrite one of evolution's greatest stories.
I found the back of a skull that I couldn't identify. It had a very good, well-preserved ear region, and that offered the clue to what it was.
The shape was familiar, but in other ways it was like nothing Gingrich had ever seen.
This is the original specimen. It's the one we found in about 1978. There are several things that strike you. One is it's very similar in size and shape to the back of a skull of a wolf.
But there was something odd about this skull. On its underside was a walnut-sized bump.
If this wasn't here, I would think that this was an archaic carnivorous mammal, what we call a creodont. But it is here.
It was part of the animal's inner ear, and it had a distinctive shape. A shape found today in only one kind of animal: whales. What was the ear of a whale doing on the skull of an animal that resembled a wolf? Gingrich was intrigued, so he constructed a model of what the creature's full skull might have looked like. He wondered, was his find a crucial missing link? The first fossil evidence ever found for one of Darwin's most daring claims, that whales had evolved from land mammals. To know for sure, Gingrich would need to find more fossils. Ones that would show each stage of the whale transformation, what scientists call transitional forms.
I want to line them all up. I want anyone to be able to see it and believe it because they've seen it.
Basilosaurus, a 40-million-year-old creature already known to science. Basilosaurus lived full-time in the water. If whales had evolved from land mammals, they had done so long before Basilosaurus. So Gingrich didn't think the bones would be of much interest. But he couldn't have been more wrong. After only a few days of digging, he made his second amazing find. It turned out that Basilosaurus had something modern whales have long since lost.
For the first time, we've got whales that have legs.
The bones were small but unmistakable. A pelvis, a kneecap, even toes. This whale had a complete set of leg bones. Gingrich brought back as much of the skeleton as he could carry. It was dramatic evidence that whales had once been four-legged animals. Since Gingrich's finds, he and others have filled in more of this fantastic story. Scientists now think that the earliest ancestor of whales was similar to this 50-million-year-old wolf-like mammal called Synonyx. Synonyx was a predatory scavenger that lived and hunted along the shores of an ancient sea. Perhaps its descendants found the water a source of abundant food and a haven from competition. Over millions of years, front legs became fins. Rear legs disappeared. Bodies lost fur and took on their familiar streamlined shape. Since Gingrich's first find, named Pachycetus, the list of known transitional whales has grown. It now includes Ambulocetus, Rhodocetus, Durodon, as well as Basilosaurus. They reveal another element of whale evolution, the gradual migration of nostrils to the top of the head as whales adapted to breathing in the water.
How did whales lose their legs?
As the years went by, they evolved into newer types of...
Gingrich's work demonstrates what Darwin himself insisted, that the evidence for evolution is all around us if we choose to look for it. And bones aren't the only evidence of whale evolution. Their ancestry is also visible in the way they move.